where I find the use of vectors very useful is solving what we call dynamics problems, so motion, things like that. So let's talk about that. So, obviously we don't always move horizontally or vertically. In fact, I suppose most of the time we're moving at some sort of an angle. So rather than dealing things going off at an angle, it's just so much easier to look at things like motion and that in a straight line. So we resolve it into horizontal and vertical and look what's happening horizontally and vertically, and then we can pull it all back together by looking at the two components to see, okay, overall what's happening. So that's sort of the idea. So first of all, here's just a simple example, but just in one dimension. So we've got a plane that's travelling south, velocity of 100 kilometres per hour, but it also has a tailwind of 25 kilometres per hour. What's the resultant velocity? How fast does that plane end up actually going? So there's our plane, it's going 100 kilometres per hour. But then, in addition, it's got this wind helping it along as well. So it's just like adding the two vectors together. So the plane would actually end up travelling at 125 kilometres per hour. Effectively, that's what it would look like. I mean, in the plane they're travelling at 100 kilometres per hour, but if we were looking at the plane, we'd think it would be moving at 125 kilometres per hour. And so in a straight line, that's a fairly simple idea. But if something happens in two dimensions, so exact same problem, but this time the wind, instead of being behind it, it's to the side of it. So it needs to be sideways. Well, what would happen there? So there's our plane going 100 kilometres per hour, but now the wind is going to the left at 25 kilometres per hour. So the effect of that, the resultant velocity, would be our black line there, or the hypotenuse, if you like. And so we could say the overall motion, well, we've got a vertical component of 100 kilometres per hour, we've got a horizontal component of 25 kilometres per hour. It would appear that this thing is moving at 103 if we work out by Pythagoras kilometres per hour. That's the sort of idea. So even though they're not in the same direction, the wind still has an effect on the motion of that plane, I guess is what we're saying. So force. Force is a vector quantity. Now, we talk about scalar quantities and vector quantities. And basically, a vector quantity is something where direction is important. So displacement and velocity and acceleration. And force, therefore, becomes a vector quantity, because you may remember that very famous Newton's second law. Force is mass times acceleration. So if acceleration is a vector quantity, force must be as well. So it has both a size to it, but the direction that that force is acting on is important as well. So let's say we've got these three forces and we've been writing the forces up in their components. So we know the first force is acting 3 units horizontally, 2 units vertically. Then we have a second force, 6 units horizontally, 4 but in the negative direction vertically. And our final force there is 2 horizontally and 1 in the negative direction. So overall, if all these forces are acting on the one particle, what's the overall thing that's happening? Well, we'd simply add up all those forces to find the result of all those forces. So we call that the resultant force, the result of all the forces acting together. And really, when we've got it like this, it's just like a bit of algebra. So we get 11 units in the, well, newtons is of course the units for force. So we get 11 in the horizontal direction times 3. 3J. A tractor's pulling the barge along a canal, and it's pulling it with a force of 400 newtons, but it's at an angle. We want to know the component of the force in the direction of the motion. Now, I said yesterday, this idea of projections, vector projections, where is it useful? In a way, this is going to be a vector projection, because we're saying, hey, what's the shadow of that force in the horizontal direction? So we're saying, what's the projection of, well, I've just called it T for tractor, on B for barge, and it would be the length or magnitude of our force, 400 times the cosine of theta, and I would be in the horizontal direction. So we'd end up with 400 cos 14. That's that. That's not in reality what I do. In reality, I just look at the triangle and imagine I'm just doing some trig. And if I said, oh, what's the length of this side? Well, it'll be 400 cos 14. I get the answer straight away. So roughly 388. So horizontal component, 388 newtons. So okay, we've got this object sitting on a plane. It's 5 kilograms. So our plane is inclined 30 degrees. We have a frictional force of 15 newtons. It's acting up there. So that's what's trying to stop it sliding down. And there's our gravitational force. Find the acceleration of the particle down the incline, but also find the reaction force. Third law. For every action there's an equal and opposite reaction, that sort of thing. Well, what that's basically saying is, look, here I am standing on a surface, and gravity obviously is acting on me. But why aren't my knees buckling? Why aren't I going through the floor? And that's because there is also a force of the floor acting on me. And it balances out, and I get to stand up, and that's wonderful. So whenever you have an object making contact with a surface, there is a reaction force perpendicular to the surface. So that's our reaction force there. Okay, well, I want to break it up into components, but you notice this time I haven't done it horizontally and vertically. So the key thing is we want to find the reaction force. So I'm pretending, if you like, reaction is, well, for want of a better word, vertical, and then down the plane is horizontal. Anything else that's happening, I want to break into components in that direction. So you'll notice my force due to gravity, which is going down, I've broken it into one going down the plane and one going, what's in the opposite direction, of course, for this vector. But it's parallel to the reaction force. We end up with a right angled triangle. Now, in that right angled triangle, the key is to work out the angles. And all we know is that there's 30 degrees for the plane, but through a bit of geometry, we should be able to identify which angle in that right angled triangle is 30 degrees. And it would be that one there. Let's see, you can play around with alternate angles and angle sums of triangles and things like that, but you need to identify which one's going to be the 30 degrees. And once we've done that, then I can say, well, the components of this gravitational force going down the plane, how I do it is I just look at it and say, where's the angle? Well, that component is opposite the angle, therefore it must be sine 30, or 5g times sine 30. And if I look at the blue one, well, that one's adjacent to the angle, so that component must be cos 30. So I don't really use that projection idea to come up with that. I just look at the triangle and use a bit of trick. So, okay, let's have a look at the forces that are acting down the plane. So, forces going down the plane, so the resultant force of everything will be, we have the components, the black one here, which I just said was 5g sine 30. And we have this other one, 15, but they're in opposite directions. Now, which one I make positive, which one I make negative, doesn't really matter, as long as I'm consistent with any vectors that are in that direction. So for this one, I've defined going down the plane to be positive. So therefore, the friction is negative because it's going up the opposite direction. Now, I can sub in all the information we know. Gravity, well, we're assuming that's 9.8. Sometimes they get you to just assume it's 10 to make the maths nice, but 9.8 is a closer one. 30 degrees was the angle, so we get that the force, mass times acceleration, is 9.5. We want to find the acceleration down the plane, so 5 times the acceleration is 9.5. So acceleration down the plane would be 1.96. I know it's down the plane because I've ended up with a positive number, and we defined going down the plane to be positive. If that somehow it turned out to be a negative number, then magically this object would be sliding up the plane. But thank goodness we got positive, because that wouldn't really make sense if we were sliding up the plane. Not without any other forces anyway. Okay. So there's the forces down the plane. The other thing it wanted us to work out was the reaction force. So let's now have a look at the forces that are perpendicular to the plane. So perpendicular, I've got R. So I've defined R to be the positive direction going up. So therefore my component, my blue component here, would be 5g cos theta. It'll be negative, it's going in the other direction. Now, we're going to sub in here. But I can sub in the force in the direction of there. The resultant force is 0. Now, they didn't tell me that information. So how did I know that the resultant force was 0? Yeah, it's staying on the plane. So we know that those forces must balance, because otherwise, just like me standing here, the forces are balancing, otherwise I'd be crashing through the floor or flying to the ceiling, depending on which direction the force was. So we know there's no resultant force overall in that direction. So we want to work out R, so we leave that as R. And root 3 on 2 is the cosine of 30. And interestingly, I didn't put 9.8 for this one. I left it as an exact value. Well, there you go. Sometimes we write them as exact values. Sometimes we round them off. And again, the force unit is newtons. Oh, there we go. So 8F is our exercise.